Hello everyone, and welcome to this video on the Sine test. This Sine test is an example of a non-parametric test or a distribution-free test, right? A test in which we do not have to have the assumption that the population takes on a certain distribution, like, we don't have to assume that the population is normal or assume that the population is chi-squared or f or any of those other distributions you may have learned about, or binomial. A non-parametric test is sometimes again referred to as a distribution-free test. This particular test, the Sine test, is used in certain situations. I'm going to go over 3 of those specific situations today and show you examples as how to perform the Sine test and how to make conclusions and use tables and whatnot. Okay, so here we go. So the Sine test, as I mentioned on the title screen, the Sine test is a non-parametric or distribution-free test that uses positive and negative signs, right? So I'll be assigning some plus signs and minus signs in a lot of these, and as you'll see that in some examples coming up. It's a test that uses positive and negative signs to test different claims, including the following scenarios. So one, well, we can apply the Sine test to test claims involving matched pairs of sample data. Right, so pairs of data that are from dependent samples, they're matched, they're related to either the same person or the same object or the same year or whatever. You'll see an example or two coming up. Or two, we could use this Sine test that I'm going to go over to test claims involving nominal data with 2 categories, right, which those 2 categories will either label as positives or negatives and then apply the test. And I have this one example of something like that. And we could also use the Sine test to test claims involving the median of a single population. Now, I know what you might be thinking, the median of a population, isn't that a parameter? And you are correct in thinking that. Remember, a parameter is a number that describes some aspect of a population. So the word non-parametric test can be a kind of misleading. It's just the standard name for these kinds of tests where you don't have to assume that any particular distribution is involved. You don't assume that the population is normal or binomial or whatever. So again, very often this is the most commonly used word for these kind of tests, non-parametric. But distribution-free is probably a more appropriate title for the kind of tests we're running here, because you'll see, oh, there is a parameter involved, a median. Right, so just be careful with that. But still, when you see non-parametric, that doesn't mean that parameters won't show up. I know it's kind of silly. It just means that you don't have to assume any particular distribution is being used. And of course, there are other situations in which the Sine test could be applied, but I'm just going to go over these particular 3 that you'll be seeing in most introductory statistics courses if non-parametric tests or distribution-free tests are introduced. All right. So what I have in the next couple pages are just the steps involved in performing the Sine test to test certain claims like these 3 I've mentioned here. And then we'll go over several examples for the rest of the video. Okay, so in performing the steps of the Sine test, the first step is just like the first step in any hypothesis testing. You're going to have a claim or a hypothesis that's to be tested, and based on that claim, you're going to be establishing, a null hypothesis, usually labeled H sub 0, and an alternate or alternative hypothesis, labeled either H sub A, or in some texts I've seen H sub 1. You're going to establish these null and alternate hypotheses based on the claim. And if you recall, the null hypothesis always involved some equality, right? Had equality involved, and this was what was to be assumed to be true. And the alternate hypothesis was either the claim itself or the opposite of the claim, and it always depended upon how the claim was stated. If the claim involves a statement involving equality, then the claim will be represented by the null, and the alternate will be the opposite of the claim. If the claim does not involve some aspect of equality, then the claim will simply be the alternate hypothesis. So again, I'm hoping you've seen if you're looking at non-parametric tests by now, chances are you've already seen basics of hypothesis testing. Next, we're going to then assign these positive and negative signs that were mentioned on the first page, plus signs, minus signs, and discard any zeros. Now, exactly what this means and how these get assigned, I will get into when we get to the examples where I apply this Sine test. Then after these signs are assigned, the value of n that we see, the value of n will be representing the total number of signs, right? So the number of plus signs I put out there, add to that the number of minus signs or negative signs I put out there. That will be the value of n in our test. Then, as with any test, you calculate a test statistic. And as you've seen, right, again, if you're here now, you've probably more than likely seen some basics of hypothesis testing, doing z-tests and t-tests and chi-squared tests, and every single time you had to calculate, pull up a test statistic to run up against, compare with some critical value, or maybe even find the p-value of a test statistic. Whatever, there were usually two methods, right? Critical value method or p-value method in hypothesis testing. Now, the test statistic for the Sine test depends on the size of this n that's mentioned here. Okay. So first you find what's going to be labeled as the value of x. Right, you're going to see this x showing up. X is the number of the less frequent sign. So for instance, if I assign 10 plus signs and only 3 minus signs, the value of x would be 3, right? Because there are fewer minus signs. The minus signs were the less frequent sign, right? And again, we'll see examples coming up. So then so after finding this x, then we can state our test statistic, and again, it depends on the size of n, the total number of plus and minus signs. So part A here, if n is small enough, right? And small enough here will be considered less than or equal to 25, right? If n is less than or equal to 25, then this x that's mentioned above here, this number of the less frequent sign, that will be our test statistic. Very simple. If the size of n is larger than 25, it's a little different. If the size of n is larger than 25, now if you want to read more up on the Sine test, you might see that this Sine test has a relationship to the binomial distribution. But again, the binomial distribution not so much mentioned. And what we have here is kind of an approximation a normal approximation to a binomial. I'm not going to get into all that. Right? Just understand that we're going to have to find a different test statistic if n is greater than 25. So if n is greater than 25, the test statistic is a z-score. All right, so remember the standard normal distribution, that z, right? The normal distribution with a mean of 0 and a standard deviation of 1. We're going to be comparing this z-score to, critical values of the standard normal distribution, just like back when you were doing z-tests, tests for means of one population and whatnot. All right. So the test statistic is a z-score, and here's how it's calculated. Z equals, and in the numerator, you have the x, right? That's this x here, right? The number of the less frequent sign, plus a half for your continuity correction. Then that value minus half of n, right? Where again n was the total number of signs, total number of positive and negative signs. So x plus a half minus half of n, and then all of that, right, all of that in the numerator divided by, and then the denominator is, the square root of n divided by 2. Now if you'd like, you could also write this, if I take this fraction here and multiply the numerator and denominator by 2, this would be, 2x plus 1 minus n, right, if I multiply each of these terms up here by 2, and then divided by the square root of n, right, where I multiply the denominator by 2 as well, and they'll cancel the 2, that little 2 here, leaving me with just the square root of n. So that's equally valid. Right. All right, so once you have your test statistic, then you're going to have to compare that to some critical value to be able to make your decisions. So we find the critical value or values. You'll see I'll have an example coming up where we have a value of n greater than 25, and it's so we're going to the z distribution, the standard normal, and it'll be a you might come across a two-tailed test, right? Remember, two-tailed tests had 2 critical values, but for the most part, when we have just when the value of n is less than or equal to 25, and you have this test statistic of x only, we're going to be going to a simple table that I'll show you that you should be able to find in most books that introduce the Sine test. So you're going to find the critical value or values from a table, and if it's the standard normal, you could also find these critical values using your calculator. Right? You see I have my TI-84 Plus Silver Edition up here on the screen. That will come into play later when we talk about finding our critical z values. And then part A, I guess, of this, and this is standard, right? This is a standard thing for your your basics of hypothesis testing. If the test statistic you find is less than or equal to the critical value, and this is for that value of x, right? Again, since you're taking the lower of the two values of the if you're taking the number of the less frequent sign. Let me go back to this here. Since this value of x is the number of the less frequent sign, we're going to use the leftmost critical value. So even if it ends up being a two-tailed test, we're still going to treat it, we're going to look at the rejection region in the left tail because of this choice of x being the number of the less frequent sign. All right. So that's why I only have this written. If the test statistic is less than or equal to the critical value that is found, then you reject the null hypothesis, right, the h sub 0. if the test statistic is greater than the critical value, right? If not this, right? If the test statistic is greater than the critical value that is found, then you fail to reject, or don't reject the null hypothesis h sub 0. And then once you've decided to either reject or not reject h sub 0, the null hypothesis, then you can state conclusions about about the claim being made, right? And I'll even show you too. I have a table where even that is kind of provided, how to word your conclusions. Now, the way I'm going to word my conclusions in this video is a very strict way. In general, as long as the language you use has the same meaning, you can use some sort of similar language. But I'm going to use a very specific language in this video to state my conclusions. Alright, so those are the steps. And like I said, very similar to any hypothesis testing steps that you'll come across, right? You establish your hypotheses, find your test statistics, find your test statistic, find critical value or critical values, and then compare your test statistic to the critical values and make conclusions. Alright, so I have some examples written out here. I'm going to go one at a time. Remember, I was mentioning on the first page this mentioning of the Sine test, how we can use this Sine test to test claims involving matched pairs of sample data and these other two. I have broken up my examples into those categories. So my first set of examples are involving claims about matched pairs of data, right? So claims about matched pairs examples. So the first example in this category reads as the following. The table below lists the customer service ratings of 10 employees before and after a training program. Right, so that's why these are matched pairs, right? Because the two readings I'm getting in the table are related to the same employee. Right, so you see employee A, his or her or their customer service rating before the training program was 7.9, let's say, out of 10. I don't know what the scale is exactly. That was not mentioned. I'm assuming out of 10. And that particular employee's customer service rating after the training program was 8.2. So you see how these are dependent values, dependent data, because they are related to the same person, right? So I couldn't switch these around, right? I couldn't move this score of 8.2 after over here to employee E, because it doesn't involve employee E, right? So let's apply this Sine test at an alpha equals 0.05 or 5% level of significance, right? Again, something you're hopefully familiar with if you've gotten to this point where you're looking at non-parametric tests. As I've said, you've probably seen basics of hypothesis testing and the mention of the value alpha, right? The significance level. So apply the Sine test at alpha equals 0.05, 5% level of significance to test management's claim that the program, this training program, improves employees' customer service ratings. All right, and here's this table. We've got the 10 employees, right? Employee, Al, Bob, Christina, Dan, Earl, Frank, George, Harry, Iris, and James, right? A through J, 10 employees, and their before and after, customer service ratings, right? Before the training, after the training. So, just as with any hypothesis test, we're going to establish our hypotheses, right? So I'll write out the steps again. 1, we're going to establish Now I'm only going to do this writing out of all the steps like this in the first example, and then just kind of write the numbers for the steps in future examples on the video. Establish the null hypothesis and alternate hypothesis. Oops, sorry, I want H with subscript of A, right? So the null hypothesis and alternate hypothesis. So remember, these hypotheses, the way they are set up, all depend on how the claim is worded, right? The claim being tested. So the claim here is made by the management at this particular company. Management claims that the program improves, right? The program improves, it's being the key word there, customer service ratings. So I guess another way you could say that is that the after ratings, they're claiming that the after ratings in general are going to be greater than the before ratings, right? Now obviously that doesn't happen all the time for each individual employee, but they're talking about, you know, overall, right? For the entirety of their employee group, right? For the entirety of the company, the people that have taken this training, it will tend to improve their customer service ratings. So another way of putting this involving these scores would be the following. You could say that the before, in general, they're saying that the before scores are less, right, if they're to be improved, than the after scores, right? Or we could say, if I did some subtraction here, you know, say I subtracted the before scores, you know, the after scores minus the before scores are greater than 0, right? If I subtract, you know, they'd be greater than 0, it should be positive. Or you could say the before scores minus the after scores are going to be negative in general. Right? Either one of these. Right? Now notice that no matter how you look at it, right, because they're claiming that the program improves, you know, bumps it up, doesn't keep it the same, there's no equality involved. There's no, you know, less than or equal to involved. There's no equality involved in the claim. So that means that this claim is going to be the alternate hypothesis. Right? If the claim does not involve equality, less than or equal to, greater than or equal to, or just equal to, then the claim is represented by the alternate hypothesis. Alright, so here I go. I'll start writing my hypotheses. So we have the alternate. Alright, that is the program improves. I'll just say the first thing, you know, in general, the before scores are less than the after scores. And again, you could write one of the other two as well, that, you know, the before scores minus the after scores will generally be negative, less than 0. Or you could write that the after scores minus the before scores will generally be positive, greater than 0. All right, then the alternate, the null hypothesis. Right, the null hypothesis does involve equality and is basically the opposite of the alternate. So if the alternate is the before scores are less than the after scores, or one of these, you know, whichever one you wrote, the opposite of is less than is greater than or equal to. So the before scores are generally greater than or equal to the after scores, right? Now you might see it written this way with greater than or equal to, but very often in most texts that I've seen, they'll use just the equal, right? Because we're going to be assuming this, right? We're going to be assuming the equality, right? You assume the equality, that the before scores and the after scores are the same, right? And this would mean that, you know, the training program has really no effect, right? You know, a way to say this in words, we'd be assuming that the training program doesn't affect or doesn't improve, right? If I really want to go with the opposite, right? Because remember, the alternate and null hypotheses should really be opposites or negations of each other. Doesn't improve scores, you know, these customer service scores. In fact, we're assuming that they're just going to stay the same in general. Now, one more way of putting this is that before minus after is equal to 0. Right. Another way to put that, but you know, so if you want to, you know, if you want to write the equals one as the null hypothesis, totally fine as well. All right. If you don't write the greater than or equal to, if you just write the equal one as the null hypothesis, that's fine, because that's what's being assumed. Right? We are assuming that the null hypothesis is true, and then going through the process of the test. Right, so again, another way of writing this is that maybe the before minus the after scores are equal to 0, or after minus before are equal to 0. All right. So that was step 1. Establish your hypotheses. The null hypothesis involving equality. The alternate here, you know, does not involve equality, and that was the claim. Right. I'm going to write that here. Right. This alternate hypothesis is the claim being tested. And that's going to be important, right? And notice that because this has just less than or just greater than, this is a one-tailed test. All right, it's a one-tailed test, and as I mentioned earlier, for the Sine test, right? I mentioned on this page, right? When we calculate the test statistic, remember this x I mentioned was the number of the less frequent sign. Because we're taking the less frequent sign, we're always going to be considering left tails, right? The rejection region on the left. All right. So when I say one-tailed test here, we're doing, you know, left-tailed test, being that this is the Sine test. All right. So that's step 1. Step 2 was assign these positive and negative signs that I mentioned. All right. Sorry, this is 2. Right? So step 2 is assign the positive and negative signs. Now, how do I do this? Well, in the matched pairs examples, right? In these, you know, like I have here, where there's these data value, these pairs of data are, you know, dependent. They rely on the same person, the same year, you know, the same individual. In matched pairs examples, you're gonna subtract, right? Subtract the first values from the second values. Right, they're the values that they are related to. In this case, in this example, that would be my after values, right? My after ratings minus the before ratings for each employee. And then we're going to assign, positives and negatives based on the sign of the result, right? And then you assign, here I'll assign plus signs to positive differences to positive results, because that's really what they want in the claim as well, right? Remember, the management's claim was that the program improves customer ratings. So remember, that means they would like the after results minus the before results to be positive. So I'll assign plus signs to positive results, and I'll assign minus signs to negative results. Now, I don't really have to use a calculator or actually do these differences. All right, let me go back up to my table, and I've got a little space below here. And in the row below the after scores, I'm going to put my plus, minus, or zeros. Right? Again, assign the positive as negative signs, and I mentioned this earlier in step 2 of the Sine test. We're going to discard any zeros, right? Because those would imply no change. Right? Just get rid of those. Now, I don't really have to subtract, right? You can if you want. 8.2, the after for employee A, minus 7.9 would be, positive 0.3. So their difference is positive. So I put a little plus sign under employee A. He had, this particular employee did have that improvement after the training, right? Like management claimed, right? That's what management kind of wants, right? You would think they would want an improvement after employee training. So you see, I don't really need to write numbers here, right? And that's the beautiful thing about distribution-free tests or non-parametric tests. Very often, numerical data is replaced by labels, plus signs, minus signs, other labels if there are out there. Now, that takes away some of the information, which is a disadvantage of parametric tests, but it gives us a general idea as to what's going on. All right. So for employee B, their score improved as well, so positive change. Right? 8.3 minus 8.0 is again positive 0.3. Employee C, their score improved from 6.5 to 7, positive change. Employee D had no change, so I'll put a 0 there, 7.1 minus 7.1. Employee E, after their training, their customer service rating went down. Right, so I'll put a minus sign. 7.7 minus 7.9 would be negative 0.2. And I do this for all these. Oh man, employee F must be hanging out with employee E, right? Oh no, wait a minute. Oops. I'm looking. I went up. I should go down. But their score improved. I apologize. I apologize to employee F. What did I say? Frank earlier. Right. So their score improved. Positive change. Employee G, the score improved by 0.1, a positive change there. Employee H also had a positive change from 8.0 to 8.5. Employee I had a positive change, 8.2 to 8.4. And employee J, J must be hanging out with employee E. They had a negative change, right? 9.0 to 8.7. That's a change of negative 0.3. So minus sign there. All right. So that was step 2. All right. Now, you assign the positive and negative signs as I have here. Did they have a positive change or a negative change in their customer service ratings? And we're going to ignore the zeros. So employee D doesn't tell me anything about how, it doesn't tell me anything toward this claim that the customer service training is improving scores or not improving them. Ignore the zeros. All right. Then step 3 was assigning that value of n. Right. As I mentioned, earlier in the steps 3. N will be called, the total number of signs, right? Again, just the plus signs and just the minus signs. So let me count these. There are 1, 2, 3, 4, 5, 6, 7 pluses. There were 7 positive changes. And there are, again, ignore the zeros, 1, 2 minuses, right? 2 negative changes, for a total of 9 signs. So that would be the value of this n here. So n is 7 plus 2, 9, right? Again, this was the total number of signs, so let's keep that in mind. All right, then step 4 in the Sine test here, step 4 was calculate the test statistic for this particular sample. Oops. Statistic. That is a T, I apologize. Now first came that value of x. I'll bring it back again. Here was step 4. Find x, which was the number of the less frequent sign. The less frequent. So if you look back here, right, at when I counted the plus signs and the minus signs, there are 7 plus signs. That's the most frequent because there are fewer minus signs. So this is the less frequent sign, right? The minus signs. So the value of this x will just be 2, the number of the less frequent signs. Okay. Then we had to worry about whether what was the size of n. N is less than or equal to 25, right? Since n is less than or equal to 25, the size of this number, the number of signs here is small enough. The test statistic is simply going to be this x equals 2. And not some z-score. Right. Okay. 5th step. All right. So after finding the test statistic for this particular sample, the 5th step, find a critical value. Right, especially when the number of signs is less than or equal to 25, we're only going to have one critical value. All right, whether it's a two-tailed or one-tailed test, right? Because we're going to have to, we took the number of the less frequent sign. We're only looking at the left side, the left critical value. So find the critical value from a table. All right, now this should be provided to you. All right, this should be provided to you, whether on an exam or some assignments. Whether you look, when you're looking through some book that introduces the Sine test to you, this table should come up. And if you don't have it somewhere, just do a quick search for critical values of the Sine test. Right, just do a search for that, and a table like this should come up. All right, so this is actually from the place I'm teaching at. This is from their practice final exam, the set of tables in the back. All right, and this table is actually incredibly nice because not only does it provide a table, we have below here the conditions under which we would reject the null hypothesis and fail to reject the null hypothesis. And then there's that z-score I mentioned, right? If the value of n was greater than or equal to 25. Notice how the table here, right? This is critical values of x for the Sine test. Notice how the first column, There's n, that's that number of signs, number of plus and minus signs together. Notice how the table I'm provided here, and in most books, again, like you're going to see, it doesn't go beyond 25, because once you're beyond 25, then you're using this z-score down here and then working with the standard normal distribution instead of this table. All right, it was mentioned to us. Right, it was mentioned to us. We were asked to use alpha equals 0.05. Right, 0.05. And then we had to pay attention. Right, I'll write this down back on the page. We'll come back to that table in a second. Remember, alpha is 0.05. And looking at the hypotheses earlier, right? Remember I said it was a one-tailed test, right? Our alternate hypothesis had just a less than in it. Right? It was just a one-tailed test. So this is in one tail, right? If this was a two-tailed test, then I'd look for in two tails. So alpha equals 0.05 in one tail. Let's go back to the table. And you see in the top here, there's alpha in one tail, and then below that, alpha in two tails, which is just double the alpha in one tail values, right? You see 0.025 here, then 0.05 below it. It's just double. So we had alpha in, it's a one-tailed test, and our value of alpha, our significance level, was 0.05. So I'm going to this row, right, with the 0.05, and the value of our n was 9, right? There were 7 plus signs, 2 minus signs. So I go down till I reach that row with a 9 for n, and then the column with 0.05 and one tail. So that's this value here, x equals 1. All right, so I'm going to write that down as my critical value. All right, so from table, I'll say xc for critical, right? C for critical was 1. And what was the value of x? X was 2. And that becomes the big question, right? Step 6, well actually, still step 5, right? So it was 5a and 5b. The big question now is the test statistic that we had less than or equal to the critical value or greater than the critical value? Right. So we see our test statistic was 2. I'll just put test stat, and the critical value is 1, and this is greater, right? 2 is greater than 1, not less than or equal to 1. So our particular sample's test statistic is not going to be in that left rejection region. Right? It's beyond that. It's to the right of it. So by my steps written out earlier, right, our test statistic is greater than the critical value, then we fail to reject. You do not reject the null hypothesis. Okay. So we're not going to reject the null hypothesis. Let's go back and see what that was again. Okay, so the null hypothesis here was that, the training program doesn't generally improve scores. That, the opposite of the claim, the opposite of the null hypothesis, the alternate hypothesis. So we are not rejecting this based on our sample. All right. So then how am I going to word this, when it comes to the claim? All right. So finally, step 6, conclusions. All right. State the conclusion. Now remember, I said earlier we had the null hypothesis, the alternate hypothesis. The alternate hypothesis had the claim in it, right? The alternate hypothesis had the claim in it that the scores generally would be improved by this training program. Now, like I said, I'm going to use some strict language here. If you word it in such a way that's similar to this, should be acceptable. Let me go back to this this chart here and look at earlier in these tables that are provided to me, and there's a little chart right here, wording of the final conclusion in a hypothesis test. Now, if you don't have this, again, that's fine. Right, if you're not privy to this, as long as you're wording the conclusions in a way that's got the same kind of language, right? This that's got a similar meaning to what I'm about to say. So you see over here, where is the claim? All right, look at the top. Where is the claim? We said the claim was in HA or H1, right? The claim that the program improved customer service ratings, we put that was in our alternate hypothesis. And then what did we decide? Based on our critical values, right? We decided not to reject the null hypothesis. So I'm looking at this first row and this second column. So here's the wording that I'm going to use. There is then not sufficient evidence to support the claim that the program improves customer service ratings. All right, so I'm going to go back to my page and write that out for you. So conclusion. All right, so again, we didn't reject this. That means there's not, we failed to reject the null hypothesis. So that means we're not supportive of the claim, right? This particular sample is not supportive of the claim. So again, the specific wording, there is not sufficient evidence. There's not enough evidence in this sample to support the claim that the program improves customer service ratings. Okay. Again, if you don't use that exact wording, that's okay. If you just simply say that there's not enough evidence to support the claim, that would be exactly the same thing. All right. There's not enough evidence, there's not sufficient evidence to support the claim based on our particular sample that we had. All right. Wonderful. Okay, so this was the Sine test. All right, and that was just one example, where I had matched pairs. I'm going to go through it again. Now this time I'm not going to write out all the words for the steps. I'm just going to write step one. We'll establish the hypotheses and whatnot, and then we'll find our test statistic, our critical value. Well, assign the plus and minus signs, then find our test statistic, critical values, and then do we reject or fail to reject the null hypothesis, and then based on where the claim is, how are we going to word the conclusion? All right. So that was example one. The next example, again, another one where we're going to be applying this Sine test to matched pairs. Now this one doesn't have a table, but you'll see that it's very much like the last problem. So here, an insurance company is comparing repair estimates from two body shops to determine whether they are different. 18 cars were sent to two different shops for estimates. Shop A's estimates exceeded, were greater than, Shop B's for 12 of the cars. And Shop B's estimates were larger for the remaining 6 cars. We're going to apply the Sine test at this time alpha equals 0.1, right, 10% significance level. to determine whether the shop's repair estimates are different. Right. So again, notice there's no table here, and there doesn't need to be. Right. But if I had a table involved, there would be these 18 cars, and I'm not going to draw the whole thing, but car 1, car 2, car 3, all the way over to car 18. And then we have the estimate that shop A gives for repairs, and then the estimate that shop B gives for repairs. All right. And again, it could be like, hey, for $500 at this, for the first car, shop A might estimate that the cost was $500 to repair the first car, and shop B might estimate that it only costs $300, and so on, right? So don't need this table, because all I need to be told, right, with this Sine test, right? Because remember, I'm not, as you saw with the last example, I'm eventually not going to need the numbers themselves. I'm just going to be assigning these labels, these plus signs and minus signs. So we already see that shop A's estimates, exceeded shop B's for 12 of the cars. So for 12 of these 18 cars, the price of A is the estimated cost at shop A will be higher than the estimated cost at shop B. And then for the other 6, the estimated cost at shop B will be greater than the estimated cost at shop A, right? So don't really need this table. All right, so first, the hypotheses, right? We'll make our claim. All right, so first what's the claim here? And what are we asked to determine? What are we testing? It says apply the Sine test with 10% significance to determine whether the shop's repair estimates are different. So that's a little different than the last one, right? The last one, there was a claim about improvement. The after scores were better than the before scores. This is simply saying that they are different. Not that one is more than the other or one is less than the other, but that they're just not equal. So the claim is the shop's repair estimate, the two shops' repair estimates are different in general for similar cars. Are different. Meaning that if I look at the shop A, right, the shop A costs, in general, they are going to be unequal to, just different to, the shop B costs. So yet again, this claim does not involve equals. It involves, not equals, but it does not involve equality. It's not is less than or equal to, or is greater than or equal to, or just equal to, but not equal. So again, this does not involve equality, meaning the claim is going to be my H1 or HA, the alternate hypothesis. All right. So here are my hypotheses: the null hypothesis, the alternate hypothesis, and again, the claim didn't involve equality, so the claim is represented by the null hypothesis. Now I'm just, instead of writing the repair estimates are different in words, I'm just going to say the shop A repair costs are different, are not equal to the shop B repair costs. And then once you've established one of these, the other one is just the opposite, right? The negation. What's the opposite of them not being equal? What's the opposite of them being different? Them being the same, right? So the shop A costs are in general equal to the shop B repair costs, right? And if I wanted to write that in words, right, that would just be the shop's repair estimates are not different, right? They are the same. And this is going to be assumed, right? The equality, right? This is going to be assumed to be true, and then we're going to test that, right? And again, this here was the claim, right? The claim is represented by the alternate. All right. Next come the signs, right, in the Sine test. Now, it already mentioned that shop A's estimates exceeded shop B's for 12 of the cars, right? So if we were to take shop A minus shop B costs, if we were to take shop A costs minus shop B costs, it would be positive for 12 of these cars, right? That's what that means. So I'll have 12 plus signs. I'll call those pluses. And every time shop B is greater, this difference would be negative, wouldn't it? Shop A minus shop B. So, I'd have the other 6 cars, right? And shop B's estimates were larger. For the remaining 6 cars, I'll have 6 minuses, right? And there were 18 cars, and so there's no zeros, right? There wasn't a car where both shops gave the same estimate for repairs. So then the value of this n is 12 plus 6, or 18. All right. Okay. That was step 3, right? I assigned the signs, and step 3 was I find the value of this n. Step 4, since the value of n is less than or equal to 25, right? The magic number 25. Oops, sorry, push this up. The magic number 25 that was at the end of that table where I found critical values. The test statistic for this particular sample of cars was equal to that value of x, right? Now remember, x here, the way it was defined earlier, is the number of the less frequent sign. Right? The frequency of the least frequent sign. So we had 12 pluses, so again, more pluses than there were minuses. So 6 minuses, right? The x equals 6, the number of the least frequent, right, sign. And that's it, right? Again, n is less than or equal to 25, so I stick with that. I'll get to one where we have to convert to a z-score in a minute. Then after that, the critical values, right? Find the critical value on that. Again, you should be able to find, and again, if you don't have it in your text or wherever you're looking, just look up the critical values for the Sine test, and you should be finding a table pretty easily online. So we had alpha was given as 0.10. Right, alpha was 0.10. We were told this, right? Alpha equals 0.1 significance level. And then don't forget what kind of test this is. Look at the claim. Look at the alternate hypothesis. Right, the alternate hypothesis involves is not equal to. So it's not one-tailed, right? This would be a two-tailed test. So this is going to be alpha equals 0.1 in 2 tails, right? Not 1, like last example. All right. So, and the value of n was 18, right? The value of n, as I showed you here, was 18. All right. So let's go to my chart and go back here, and we'll go to this chart. That's the hypotheses. I'll go back down to where it's the critical values of the Sine test. Here we go, critical values of x for the Sine test. N was 18, right? So this row and the column we're going to go to has alpha, it's a two-tailed test this time. So I'm looking at this alpha in 2 tails, and alpha was 0.1. So 0.10, that's 0.1 here. So this column to the row with 18, the critical value is 5. 5, right? X equals 5. So back to my page. We're seeing from the table that XC, right? I'll call XC the critical value, that's 5. And what was our test statistic? X was 6, right? X equals 6 was our test statistic. Our critical value was 5. And, is the test statistic less than or equal than the critical value or greater than? And it is greater than again. All right, it is greater than again. So, according to the table, the instruction under the table, we would fail, just like last example, we would fail to reject the null hypothesis. Yet again. Okay. And then the conclusion is going to be the same as the last time. All right. When I state the conclusion, it was the same as the last one, where you see my claim. It all depends on where the claim is and whether or not we rejected or failed to reject the null hypothesis. The claim was in the alternate, and we didn't reject the null, right? So we kind of stuck with the null, right? Meaning our evidence does not support the claim, right? So just as the last example, I would say that there is not sufficient evidence to support the claim that the shop's repair estimates are different. And again, if your word is something similar to this, there is insufficient evidence to support the claim, there isn't enough evidence to support the claim. Either one of those, as long as it has the same meaning, it should be a valid conclusion. All right, so now let's get into another example. Okay, so another example where we're going to have kind of a matched pairs situation. But this time you'll see that we'll end up with a value of n that's greater than 25, so I won't be able to use my table to find critical values. So I can go to the calculator or another table, right? The table for the standard normal, the z distribution. So here, an ice cream company has developed 2 new flavors and invites 90 customers to taste both and identify the flavor they prefer. 53 customers preferred flavor A, 27 customers preferred flavor B, and 10 could not decide, so they didn't prefer one over the other. They didn't know. Right? They were equally good in their eyes. So I'm asked here to apply the Sine test to test the company's claim that there was a difference in customer preference, with the significance level being 1% this time, 0.01. Now, just as before, you might be thinking, hey, how is this like a matched pairs thing? Well, this is just like the last example with the cars. I could make a table here where I have customers, right, and then it's customers 1 through 90. Right? You see why I didn't want to have to make a table here. There are 90 customers, and there's these 2 flavors, flavor A of ice cream and then the flavor B of ice cream. And suppose, when I talked about their preferences, maybe I had each customer give the ice creams a score, like out of 10. Like, how would you rate flavor A, customer 1, person number 1? How would you rate flavor A out of 10? 7.1 out of 10. customer one, here, try this flavor B. How would you rate that? Oh, I'd rate it 8.9. I liked it better. Right, so they preferred flavor B. And you see now how it would be kind of, I would do this down the line, do it for customer two, and I'd get these matched pairs of data, that are related to a single individual. Just like for the first two examples I showed you with the shop repair costs and the customer service ratings. All right, so very similar. All right, so instead of looking at a table, right, we'll just refer back to how many said they preferred one flavor over the other in the problem. All right, so first, again, the hypotheses. Well, before you can set up your hypotheses, you have to know what's being tested. What's the claim being made, or the hypothesis being tested? So again, the company is claiming that there just was just a difference in the customer preference. They didn't say, oh, more customers preferred flavor A or more customers preferred flavor B. They're just saying that there was a difference. All right, they're not pointing out one way or the other which ice cream flavor was mostly preferred. So the claim is there was a difference. Or there is a difference in customer preference. Now, if you relate this claim to my little scores, say I gave flavor A and flavor B, flavor scores, that would mean basically that the flavor A scores in general were different in some way, so were not equal to the flavor B scores. All right, so yet again, all right, I kind of just picked these problems at random out of a couple books I have, just to demonstrate the Sine test. Hopefully we come across some claim that involves equality. I probably should have read them more carefully. I apologize, but one of these times I'm sure you're going to come across a claim that actually does involve equality. But right here again, our claim does not involve equals. It's not equal. So again, the claim does not involve equality. Is less than or equal to, is greater than or equal to, or is equal to. So yet again, the claim is the alternate hypothesis, that HA or H1. All right, so that when I set up the two hypotheses, null hypothesis, alternate hypothesis, the claim is the alternate, that the flavor A scores are different than the flavor B scores, and that's it. Right, that there just is a difference in customer preference, if you want to write it out in words. And then remember, these alternate and null hypotheses are just the opposite of each other, just negations. So if the alternate hypothesis is that they're different, the null hypothesis is that they are the same, right? And the alternate the null hypothesis should always involve equality, right? And this is what's going to be assumed to be equal, assumed to be true. Right? We're going to assume that there is no difference, and then see if we agree with that or not. Okay. And this, again, the alternate hypothesis is simply what's being claimed, right? The hypothesis being tested. All right, so I've got my hypotheses set up. Then I'll go through and assign the signs. All right, the plus signs and minus signs for this Sine test. Again, I don't have a little chart with me like the first example, but I do have enough to say some things, right? If I were to take, let's say, now again, I got to assign my plus signs to something, right, and minus signs to mean something else. Let's just say a plus sign means that flavor A was preferred over flavor B. Right, and then the minus signs will mean that flavor B is preferred. Or you could also write this in terms of flavor scores. If you took flavor A score minus flavor B score, if it's positive, I'll give it a plus sign. If it's negative, I'll give it a minus sign. And if there's no preference, we'll call that 0. Right? No preference. All right. So reading back through the problem, it mentioned of these 90 customers, 53 customers preferred flavor A. So that means I'm having 53 labels of pluses, right? 53 pluses. And 27 preferred flavor B, so I'll have 27 minuses. Right? And 10 could not decide, so 10 zeros, right? 10 O's. All right. Now the only ones that matter here to me, again, you ignore the zeros, are these two, right? The pluses and minuses. So part 3 was, what's the value of that n? It's 53 plus 27, right? Just the number of signs that are not 0, the number of pluses and minuses. So that's 80, all right? So n is 80. Now that's, that's not going to be on my table, right? That's greater than or equal to 25. All right, so part 4 was finding the test statistic, right? First I found that x, remember x was the number of the less frequent sign of plus or minus. There are more, again, this isn't always going to happen. I hope you know this. There aren't always going to be more pluses and minuses, just be aware of that. But here again, there are fewer minuses. There are 27 of those, right? So I picked the less frequent. And something else I'll point out too, back in the alternate hypothesis, this is another two-tailed test, right? It involves is not equal to. Right? They are different. The claim was that there was a difference. There is a difference in customer preference. So just pointing that out that this is two-tailed. Now, unlike the first two examples, this x equals 27. This is not the test statistic. Since the value of n is beyond my table, right? My table of critical values, n is greater than or equal to 25. The test statistic, we're gonna work with the z distribution instead. Right? We're gonna work with z-scores and the standard normal. The test statistic will be a z-score. Z equals, again, I'll write it out one more time here. X plus 0.5 minus n divided by 2, and then all of that divided by the square root of n divided by 2. Or, like I said, if you multiply the numerator and denominator of this by 2, 2x plus 1 minus n, all of that divided by the square root of n. Either one's fine. All right, so let's calculate this. Now, we already have the x and the n, so this should be easy. Right? So we have our test statistic is a z-score. Z equals, 2 times x, so 2 times 27, plus 1 minus n was 80. All right, all that in the numerator, divided by the square root of 80. All right, and I'm going to round this. I'm going to go to my calculator, round this to 2 decimal places, let's say. All right. So over here on my 84, so now 2 times 27, I can do the numerator in my head, right? That's 54, plus 1 is 55, minus 80 be negative 25. Right? So I have negative 25 in the numerator, right? And then divided by the square root of 80. All right. So about negative 2.8. Approximately negative 2.8, if I round to 2 decimal places, 0.795 there, bump that to 0.8. All right, now when I go to find critical values for part 5, and remember this is a two-tailed test. Now when I go to find critical values, since my test statistic is a z-score, we're talking about critical values from the standard normal distribution. not from that other table, from the standard normal distribution, right? That z distribution. Now there are a couple ways you can do this. Remember, for the standard normal, right? That was, if you drew a little picture with a bell-shaped curve, right, with a bump. Remember the mean was 0, standard deviation was 1. Our value of alpha here, right? The alpha given, the significance level from the problem was 0.01, right? 0.01. And remember what alpha was. That was the total area of the rejection regions. When you were talking about area under a curve. Now, being that this is a two-tailed test, I'm going to cut this in half, right? We're breaking it into two pieces. Now, if alpha is 1%, half of alpha was, half a percent, 0.005, right? And we're looking for these scores, right? What is, I'll call this ZC, and I'll call it, for critical, Z critical, and then over here is negative ZC for, the opposite of Z critical. We're looking for these values such that the area, either in the left tail or in the right tail, is 0.5%, right? That way the total area of all the rejection region is my alpha, is 1%. All right, now there were a couple ways to do this. Okay, there were a couple ways to do this. One was with a table. So let me go back and show you. All right. Now again, the table, now not this table, right? Not the table for the Sine test, but the table for the standard normal, right? For z-scores. So I got to scroll up a bit. All right, and again, if you want to do a Google search for this, so here we are. Now notice my table here is for cumulative area to the left of z-scores in the standard normal distribution. All right, so I'm going to look for the z-score that has an area of 0.5% to the left. So that'll be this z-score here. All right, this negative zc. Right. And then the opposite of that will be the other critical value, right? That has an area of 0.5% to the right. All right, so back to the table. Now a z-score with 0.5% to the left would be negative. So I'm going to go up here to where there's negative z-scores. And I'm looking in the area, I'm looking in the table here until I find, now the beautiful thing about this is, look at the bottom. There's some notes in this particular table. The area of 0.005 to the left corresponds to a z-score of negative 2.57. So I don't even have to look in the table. It's told to me down here what z-score has an area of 0.005 or 0.5% to the left. All right, so that's beautiful. So this score here is negative 2.575 according to that chart, and then this score would be positive 2.575. All right, and those are our critical values. All right, those are our critical values. Now, another way you could find this, all right, another way you could find this was using the calculator and the inverse normal. So if I go to my calculator here, if you go to above the variables button, there says distribution, second distribution. And you want to find, what particular score has a particular area to the left of it. I go to inv norm here, number 3. And then, what's the area to the left that I wish? 0.005, right? That was my half alpha for the left tail and the right tail. And it's a standard normal, so mu 0, sigma 1. And I'm getting, again, see, negative 2.57. It's closer to 6, but not going to be that much of a change, right? So negative 2.575, negative 2.576 if you were rounding to the nearest thousandth. Either one is fine. So I'm going to use the one that was given to me from the chart. Now, as I mentioned before, for this sine test, I mentioned before, for this sine test, we're going to compare to the left one, all right? Because remember, x, the value of this x was the number of the least frequent sine. So I'm already thinking left. I'm already thinking less. Because I chose x to be the number of the least frequent sine, we're going to compare to the left critical value, right? Basically change this into a kind of a left-tailed test. If for some reason you chose the number of the most frequent sine, then you'd compare to the right one, right? But for the sine test, we're going to compare to the left critical value. Z equals, negative 2.575. All right, so let's do that. What was our test statistic? I said it was around up here, right? This negative 2.8. Right, Z test. Our test statistic was negative 2.80. Our critical value, I'll say Z crit. Again, I'm comparing to the left one, negative 2.575. And be careful with negatives, right? Remember, this is more negative than this, right? So this is actually less, right? When you are more negative, think about being more in debt. It's worse, right? This is less than or equal, right? It's less than this critical value. So this time it is satisfied. My test statistic is less than or equal to the critical value. So for this example, we do reject. We actually reject it. We do reject the null hypothesis. All right, and so then what does that mean for our conclusion of the test? What does that mean for the conclusion? All right, so again, going back to my little chart here, let me show you the work. Now, you probably can guess it. Before when the claim, right, when the claim is in the alternate, and we didn't reject the null, then there wasn't sufficient evidence to support the claim. This time, the claim is in the alternate, right? So see the original claim is in H1 or HA, but this time our decision is to reject the null hypothesis. So instead of not having sufficient evidence to support the claim, there is sufficient evidence to support the claim. Great. All right, so I will write that here. So this time again, the claim was in the alternate, and we're rejecting the null. So I'm not accepting this. Cross it out. We're accepting the claim. So we're saying that for this particular sample of 90 customers, the claim is supported. Right? This time there is sufficient evidence. And I guess a really off-putting way of saying that would be there isn't insufficient evidence, like a double negative. You could write that if you want. Or there is enough evidence. There is sufficient evidence, V. There is sufficient evidence to support the claim, and the claim that there was a difference in customer preference. And that's how I would end it. Great. All right. So all of these examples involved matched pairs, right? Two values, two readings, two pieces of data that related to the same object, right? The same car, the same customer, the same employee. So my next examples, well, I just have one of these. The rest of these should be pretty simple. They're all done about the same way. Right? The way I just did those first three examples, doing pretty much exactly the same way. Now this is a claim about, nominal data, data that's only got labels, which I guess you could have called the last one as well, with the I prefer flavor A, I prefer flavor B, right? There's really, you don't have to have numbers for that. And even so, the numbers would be nominal because they are more of a label than anything. All right, so here's an example specifically about, where we're going to be testing a claim about nominal data. All right. So before the overtime rule in the National Football League, the NFL, right? Before the overtime rule was changed in 2011, among 460 overtime games, 252 were won by the team that won the coin toss at the beginning of overtime. All right, meaning that the other 208 games were lost by the team that won the coin toss. Hope that makes sense. All right. So apply the Sine test with a significance level of 5% this time, alpha equals 0.05, to test the claim that the coin toss is fair. Not that it's going to come up heads or tails 50-50, but in the sense that neither team has an advantage by winning it, right? So we're going to test the claim is that, winning the coin toss doesn't give you a significant advantage for winning the game, which you might think it would, because remember before the overtime rule was changed, it was whoever scored first, whether it be a field goal or a touchdown, that was it, game over. Now if the first team scores a field goal, then the other team can come back and try to score, and it's different now. But back before 2011, it was first team to score wins. So you would think that if you did get the ball, if you won the coin flip, you'd probably choose to get the ball and probably have a better chance of winning. But let's see what happens based on this particular data. All right, so this time again, same thing. I'm going to start off with my hypotheses. What's the claim? All right, we'll start with the claim because you can't establish your hypotheses unless you know the claim or the hypothesis being tested. The claim is that the coin toss is fair. I'm just going to write that. Right? The coin toss is fair. Meaning it, winning the coin toss doesn't give you an advantage. All right, winning or losing the coin toss. Winning coin toss doesn't give advantage to any particular team. All right. So the claim is that the coin toss is fair in that sense. All right, so another way of putting that is that you would expect the number of teams, if you want to put it in terms of maybe numbers, if the coin toss truly doesn't give anybody an advantage, that means we would expect that the number of teams who won the coin toss won the game. The number of teams that won the coin toss that won games is about the same as the number of teams who lost the coin toss but still won the game. Right? Or the number of teams who won the coin toss and lost the game. Same number. Right? So number of teams that won the coin toss that lost the game. Right? We're expecting that these are equal, is what they're saying by the coin toss is fair. Right? That winning the coin toss gives you no advantage either way. You have the same chance of winning and losing the game if you win the coin toss. All right. So notice that the way I'm wording this, the way this is worded, as I'm seeing it now, this claim does involve equality this time. All right. So the claim involves equality, meaning the claim is going to be represented by the null hypothesis this time. Remember, the null hypothesis always involves equality. So I set up my hypotheses, and I'm just going to write very simply, the coin toss is fair. That was the claim. All right, meaning that you would expect, again, the number of teams who won the coin toss that won the game to be about the same as the number of teams that won the coin toss that lost the game. And what's the opposite of that? Right? The null, and again, this is going to be assumed. We're going to assume that it's fair. You always assume that the null hypothesis is true, and then make a decision later on based on the test statistic and critical values and all that. And the alternate hypothesis is, the opposite of that, the negation of that. The coin toss is not fair. Or the number of teams, that these are different numbers. We're saying that the number of teams that won the coin toss that won the game is not about the same as the number of teams that won the coin toss that lost the game. There's a difference there. Some team gets an advantage over another with this coin toss. All right, so the coin toss is fair, coin toss is not fair. All right. Now, assign the signs. All right, so this time I'm going to say plus sign is for teams that won the game when they won the coin toss. It's like a positive outcome. Again, you assign them however you like, really. Teams that won the game, that won their game after winning coin toss. Because that is a nice positive outcome. And I'll minus sign for teams that lost after winning coin toss. All right. A little repeat, ditto signs. And then I guess zeros would be for teams that tied, but they didn't mention any of that. All right, so I'm not going to put in zeros here. So what we're seeing from our problem, right? Again, there's no table or anything, but they said among these 460 team overtime games, 250 of those games were won by the team that won the coin toss. So I have 252 pluses, because there were 250 teams that won the game after winning the coin toss. And let's assume there's no ties here, right? They didn't mention anything about ties. So the remaining games were lost by the team that won the coin toss. So 460, minus 252 would be 208. Right? So there'd be 208 minuses. Right? 200 teams that won the coin toss but still lost the game. And again, no ties. Don't worry. We're not worried about ties here. So the value of that n, I guess part 3. Right, the value of that n is just 252 plus 208. Is the 460. So notice that is much larger than our 25 from the chart, from that table of critical values. So we're going to again be doing that z-score calculation and comparing the critical values. And also I want to point out, I keep forgetting to point this out right away. Right, remember the null hypothesis would be they're equal. You would expect these things I wrote up here to be equal. So the alternate hypothesis, you'd expect them to not be equal, so you'd have a not equal sign involved, meaning that this test is two-tailed again. All right, this test is two-tailed. Let's keep that in mind when I go to calculate critical values later. All right, fourth part. So first I find that x, remember x is the number that's the least frequent, so the 208 minuses. And then since n is greater than or equal to 25, our test statistic, I'll just put test stat, is going to be a z-score. Right, z equals, and I'll do that simplified version, where it was 2x plus 1 minus n, and then all that divided by the square root of n. All right. All right. Now we know x and n. Right? So the z-score, our test statistic, is 2 times the x was that 208, the least frequent of the sines, that number, plus 1 minus n is 460. And this gets divided by the square root of 460. All right, just as before, I'm going to round this to 2 decimal places. All right, so in parentheses, 2 times 208 plus 1. I guess I just put minus 459, but minus 460. All that in parentheses in the numerator, divided by, and then the square root of 460 in the denominator. This is approximately negative 2 point, I'll just go 0, 0 if I'm going to 2 decimal places. So about negative 2. All right, about 2 standard deviations away from the center, right, to the left. And then for critical values, again, there were more than 25 here. N was greater than or equal to 25. And there are going to be 2 values. This was a 2-tailed test, as I mentioned before. So if you're thinking of the standard normal, right, that z distribution, I'll draw a little picture again. Doesn't hurt. Remember there would be 2 rejection regions, one in the left tail, one in the right tail. And we're looking for this, z. I'll call this zc, and this negative zc for critical values. And remember what alpha was here. All right, now alpha for this test was 0.05. Right, alpha 0.05 from my problem, 5%. Alpha was 0.05, and we're doing a 2-tailed test, so this gets cut in half, right? Alpha divided by 2 is 2.5%, right? 0.025, and that's the area in both these tails, right? 0.025 to the left of that value that I'm going to find, and 0.025 to the left of that value that I'm going to find. All right, so again, I'm just going to do the calculator this time. All right, again, you can find these values in a table like I showed you before, but I'm just going to use that inverse normal this time again. So distributions, inverse normal, and then that 0.025 area to the left that I'm looking for, mean 0, standard deviation 1. That's how you'd have to enter it if you had an old one with some commas. So negative 1.96. Right, let's say this is negative 1.96 and positive 1.96, right? So these are the critical values. Let's say CVs for critical values, okay? CVs. But don't forget, we're doing this sine test. X was the number of the less frequent sine. So we're always doing the comparison to the left critical value, right? So then for 6, compare them. Oh, 6 is a conclusion, sorry. So our test statistic, right, so z test was this negative 2.00. And our critical value, say z crit, is, again, the left one compared to the left one, negative 1.96. And again, this is less than or equal. Our test statistic is, more negative than this negative, right? So this is less than or equal. It's less than our critical value again. And because that's happening, we yet again reject the null hypothesis. All right. So this one's a little different. All right. This one's a little different than our previous examples because this time the claim was in the null hypothesis, right? The claim was represented by the null hypothesis. It had equality involved. But we rejected it, right? Put a little cross through that. Scratch this out. The claim was in the null, and we rejected the null. So how do I word my conclusion this time? All right, so going again, if your wording is in a similar language, that's fine, but let me show you a more scientific, more proper wording. So again, this time, looking at this little chart, my claim was in H0, right, the null hypothesis. and our decision was to reject the null. So there is sufficient evidence. There is enough evidence in our sample to warrant rejection of the claim. Right? So there's enough evidence to reject the claim, right? Because the claim was the null this time and we rejected it. So there's enough evidence to reject the claim. We are not we're not in support of the claim, I guess you could say. All right. We don't agree with the claim, is what that's saying, right? But again, the more proper wording, which I'll write out here, right? So the conclusion, so there is sufficient evidence to warrant rejection, right? Warranting rejecting of the claim. To warrant something is to agree with it. I warrant that was warranted. That should be allowed. To warrant I should allow rejection of the claim, right? I agree with rejecting the claim. I don't agree with the claim itself. Warrant rejection of the claim that the coin toss was fair. All right. So if we're saying this, right, we're saying there's enough evidence in our sample, those 460 overtime games, to warrant rejection of the claim that the coin toss is fair, then we're saying that the coin toss wasn't fair, and thus the rule change, right? Because I'm sure they had people look at those just like this. They had people look at those overtime games and talk about the coin toss and whatnot, and determine, hey, that coin toss isn't fair. Just because you win the coin toss, you're going to take the ball, you're probably going to win. Let's change it up so the other team has a better chance as well. That's why the rule change came about, right? Because of something like this. Somebody made this kind of statement after a test like this. I don't know if this was the exact testing they did, but they obviously came to a similar conclusion because the rule got changed. Great. All right, and now my last examples. All right, my last examples of this Sine test involve that third kind of claim, right, which was claims about the median of a single population. All right, claims about the median. All right, now remember the median of a set of data was the value that's exactly halfway in the middle. Now, if you were to arrange all the values in the population in order, the median cuts the upper half from the lower half, right? 50% above, 50% below. All right, so here, this will involve a claim about the median of some population. And I've got two of these. All right, first off, the table below shows the electrical usage in kilowatt hours, kWh, of 12 homes during the month of February. Right? What year? I don't know. Apply the Sine test to test the claim that the median electrical usage is more than 1,000 kilowatt hours, using alpha equals 5% this time. All right. So here I got just 12 numbers here, number of kilowatt hours per house. Say again, just 974, 815, 13, 20,000. Again, just 12 numbers for the 12 different homes in my sample. Right. So just like any test, one, we'll establish the hypotheses. So first, in order to establish the hypotheses, you need to know what claim is being tested, what hypothesis is being tested. The claim is that the median electrical usage is more than, keywords there, right, 1,000 kilowatt hours, right? And this is a claim about the entire population. I hope that's understood, right? Every time you make a claim, when you're doing hypothesis tests, it's about some population or some populations. Right, so this is about the entire population of people using electricity in this town or state or whatever this is. Now, if I want to put this in another way, using some symbols, this is saying that the median electrical usage, I'll just say median, is greater than 1,000 kilowatt hours. So a median is greater than 1,000. Another way to put it, if you want to just manipulate some stuff, the median minus 1,000 is greater than 0. Or 1,000 minus the median is less than 0. You want to put it all sorts of different ways. But notice that this claim, this hypothesis we're testing, does not involve equality. Right? There's no is equal to. There's no is less than or equal to, is greater than or equal to. Does not involve equality. Right? Because of this, this claim will be represented by the alternate hypothesis. All right, so let's set it up. Null hypothesis, alternate hypothesis. All right, like I said, this is the alternate hypothesis, that the median is greater than 1,000, or the median minus 1,000 is greater than 0. All right. And remember, the alternate and null hypotheses should be negations of each other, opposites. What's the opposite of greater than? It's less than or equal to. So the null hypothesis is that the median electrical usage is less than or equal to 1,000 kilowatt hours. Now again, you could also just state what's going to be assumed. All right, we're going to be assuming just the equal part of this. Assume that the median equals 1,000 kilowatt hours and go from there. So if you just wrote that the median was equal to 1,000 for the null hypothesis, that would also be acceptable. Okay. And I'll make a point to say that the claim is down here, right? The claim is in the alternate hypothesis this time. And looking at the symbol, I'll actually point it out on time here, the symbol is greater, just greater than. So we have a right-tailed test. Well, normally this would be right-tailed. I'll say right-tailed normally. All right, if we were working with the normal distribution or some other chi-squared ft normally, but I'll just say one-tailed. Okay, one-tailed for the sine, because remember. So I'm going to ignore the right-tailed for now and just say one-tailed, but it is one-tailed. Because remember, with this sine test, as I mentioned already, the value of that x that I'm using is the number of the less frequent. So you're always working with left side, left side, left side. So even though it looks like the way I've set it up, right-tailed test, we're going to call it a one-tailed test when we go to find critical values later. All right. Okay, 2, the sines. Now, for a median test, for these tests involving claims about a median of a single population, we'll just subtract the median from all the values. All right, like I said here, median minus, remember we're assuming the median is 1,000. Remember, this is being assumed, the null hypothesis. We're assuming that the median usage is 1,000 kilowatt hours. Subtract the median from all values in the sample. And I'll assign a plus sign to positive results. Makes sense. And I'll assign a minus sign to negative results and 0 to 0. I'm not even going to write the 0 one. All right, so let me go back to my chart, right? I had this sample of 12 households and the electricity they used in the month of February. Now, if I subtract the median, now remember, we're assuming the median is 1,000. So I'm going to subtract 1,000 kilowatt hours from each of these. And I'll make a point of that here. Right? Let's subtract 1,000 and see what happens. This would be a negative result, right? 974 minus 1,000. This would also be a negative result, right? Because again, it just basically if the kilowatt usage is under 1,000, it's below. It's a negative result. And if it's over 1,000, it's above. It's a positive result. And if it's equal to 1,000, it's a 0. This is above, positive. This is actually the same. So I'm going to ignore that. Remember, we ignore the zeros. This is below, minus, above, plus, above, plus, above, plus, above, plus, above, plus, above, plus, and above, plus. Wow, look at that. Okay. So, these 12 households, I'm going to count the signs. You have 1, 2, 3, 4, 5, 6, 7, 8 pluses, 3 minuses, and again, a 0 I am going to ignore. So I have 8 positives, 3 minuses, and a 0. So then that n, third part here, that value of that n is 11. Right? The value of n was simply the number of signs, plus and minus signs that show up. So n equals 11. And then for our critical values, right, again, we find that x is 3, right, the less frequent of the two signs. And since this, it's been a few examples here, but since n is less than or equal to 25, I can actually find a critical value on that chart, right, the critical values for the sine test. So the test statistic is this x, is just x equals 3. Okay, wonderful. All right, then critical value, let's say x crit or xc. So I go to the chart. Now don't forget it's a one-tailed test, and alpha, right, alpha is 0.05. So alpha is 0.05 in one tail. Right, so 0.05, keep that in your head, 0.05 in one tail. So I go to my chart there, back down to that critical values for the sine test. Here we are, critical values of x for the sine test. Alpha in one tail, right, 0.05. And the value of n was 11, right? 8 plus signs, 3 minus signs. 11, 0.05 in one tail. Look at that row in that column. You get a critical value of 2. Right, a critical value of 2. All right, so our x test, right, our test statistic is 3. And you see the test statistic is greater than the critical value, not less than or equal to. Right? The test statistic is greater than the critical value this time. So we do not reject the null, right? We fail to reject the null hypothesis. All right. And then the conclusion. All right, then the conclusion. So remember, going back up here, this is another one of those where the claim was in the alternate, but I didn't reject the null. I kept it. I failed to reject it. I'm accepting the null. I am not accepting the claim. Right? So the way that was worded was, there is not sufficient evidence to support the claim, right? To support the alternate hypothesis. So there is not sufficient evidence, or not enough evidence, or insufficient evidence, however you want to word it, as long as it's equivalent. There is not sufficient evidence to support the claim that the median electrical usage is more than 1,000 kilowatt hours. All right. Great. All right. Now I've got one last example that you bear with me here. I'm going to breeze through this one, all right, because you should hopefully have seen enough by now to see where I'm getting these numbers from. So one last example. This is again involving a claim about the median. So a commuter would like to test a hypothesis that her median commute time is less than 30 minutes. Of her last 45 commutes, to and from work or wherever she's going, 27 were shorter than 30 minutes. 16 were longer than 30 minutes. Apply the Sine test to her claim using, alpha equals 0.01. All right, so I'm just going to set up the hypotheses here. Now the claim is this hypothesis she's testing. She wants to test the hypothesis that her median commute time is less than 30 minutes. Less than. Notice that does not involve equal to. So that's going to go in the alternate. Her median commute, I'll just say median. Her median commute time is less than 30 minutes. One-tailed. Right, the way that there's just a less than, that's a one-tailed test. Normally we'd call it a left-tailed test, but for the Sine test, it's a left-tailed. All right. Again, normally left-tailed. Right. All right, and then the null hypothesis would be that the median is the opposite of this. The opposite of is less than is greater than or equal to 30 minutes. But you could also just write equal, right? And that would be equally valid. Just because that's what we're going to be assuming. We're going to be assuming that her median commute time is actually equal to 30 minutes, right? And again, the claim is down here in the alternate again. Right. The signs. All right. I'm going to assign a plus sign if the commute time is more than 30 minutes. I'm going to assign a minus sign to a commute time less than 30 minutes. And a 0 if she has a commute time equal to 30 minutes. All right, so 27 were shorter than 30 minutes, so that's 27 minuses the way I have set up the labels here. 16 of those 45 commutes were longer than 30 minutes, so 16 pluses. And that's only 43, so there would be 2 zeros, I guess. If there's 2 commutes she took that were exactly 30 minutes. All right. But all that matter are the pluses and minuses, right? In my Sine test, I'm ignoring the zeros. All right, so the value of n. The value of n is the number of signs, the plus and minuses. Again, like I said, that's 43. The value of that x, right, the least frequent of these, this time the pluses are least frequent, is 16. And yeah, since n is greater than or equal to 25, my test statistic is that z-score, right? That z-score one with the 2x plus 1 minus n divided by the square root of n. So that's 2 times 16 plus 1, so 33, right? 32 plus 1, 33 minus 43 divided by the square root of 43. So that's negative 10 divided by the square root of 43, which I'll get rounded here. So I'll just do 10 and just make it negative 10 divided by the square root of 43. And make it negative. Negative 1.52, right? Approximately negative 1.52, right? So there's my test statistic. critical value. Remember, this is only a one-tailed test, and we're always doing it the left side, right? Because x was the number of the least frequent, we're always going to the left side. Right? Critical value, right, if you're looking at the standard normal, little picture of a bell shape here. My critical, again, only one tail. I'm only looking for this one value, right? Just one value this time. And the value of alpha was 0.01. So 0.01 for the area to the left. I don't cut it in half, right? This is just one tail this time. So I go to my inverse normal, right? Distribution, inverse normal, area to the left 0.01, mean 0, standard deviation 1. Okay, so this critical value is negative 2.33, approximately negative 2.33. And then comparing these two, negative 1.52, my test statistic is greater than negative 2.33, right? It's not as negative, it's more to the right on the number line. And so my test statistic is not less than or equal. I'm not in the rejection region, right? So that means we do not reject, we fail to reject the null hypothesis. And then my conclusion, right, just again pay attention to where the claim was and whether or not you failed to reject the null hypothesis. The claim was in the alternate. Again, I didn't reject this. Right? I didn't reject the null, so I'm keeping it, meaning I'm not supporting the claim. All right, so like the last one, there is not sufficient evidence to support the claim that her median commute time is less than 30 minutes. But I'll just write there is not sufficient evidence to support the claim that she made, right, that she was testing. All right, and I'm done. All right, and that took a few minutes. They really can be that quick if you know what you're doing. So I'm hoping that after watching these, I think I had like 5 examples throughout this. No, 6 examples throughout this, and there's plenty more out there. Right, just look up Sine test and maybe Sine test exercises. Do a search or look in your book if if your book has exercises involving the Sine test, right? That non-parametric test, and go to town on it. Right, it's the only way you're going to get good at anything. It's by practicing. All right, so I hope you enjoy practicing problems of this nature, and thank you very much for watching.